All right, the topic of today's lecture is conservation of momentum, section 9.2 of your book. And conservation deals with mainly things that collide and things that separate, so collisions and separations. Now, momentum is always conserved whenever things collide and whenever things separate, if and only if you have a couple of there are a couple things true. Number one, the system has to be closed. When you have a closed system, that means that you're not gaining or losing mass. So no mass lost or gained. So if you have a collision, you can't lose mass and you can't gain mass. So if the mass isn't messed with, we call it a closed system. And another thing is it has to be isolated. An isolated system is when there's no outside forces interfering. And if these two things are true, if you have a closed system, if you have an isolated system, then you can say that momentum is conserved. Momentum is conserved. And when we say that momentum is conserved, what we mean is this, that there's usually an event. And there's something before, prior to the event, and after the event. So think of collisions. So before the collision, you have two cars or anything collide, two football players. And then after the event, you've got like they either stick together or they hit each other and bounce off. That's after the event. So you're going to have a before and you're going to have an after. And the momentum before, and a lot of times we write it like this. So the momentum before, and this is the Greek letter rho, is equal to the momentum after. And it's the momentum of all the pieces. So if you've got like multiple things colliding, you add up the momentums beforehand and they have to equal all of the momentums afterwards. Same with separations. Like for instance, like firing a gun. Like if you shoot a gun, you get this like kick. That recoil, the momentum before and the momentum after are the same. So before, the gun is just still, and then after, you've got the bullet going to the right and the gun going to the left, and the momentums will be the same. For instance, let's say, your example, this is example problem number 2. From your book, and I'm on page 237. So let's see if we can see this idea of an event. Before the event, after the event, add up all the momentums before. They have to equal all the momentums after, if and only if it's closed and it's isolated. So let's read what it says. We've got an 1875 kilogram car. It's going pretty fast, and it rear ends a smaller car that's going slower. It's on ice in the same direction. The two cars stick together, so I'm assuming that the ice means that there's no friction. Maybe there is, but it says, how fast did the two cars move immediately after the collision? So here's our event, is the collision. So before the collision, so before it, we've got a large car going this way at 23 meters per second. And this thing is 1875 kilograms, and it rear ends a smaller car that's still moving, but it's only moving at 17 meters per second. And this smaller car is 1025 kilograms. So before, this is everything, and then after, they stick together. So afterwards, I've got my big car stuck to my small car. So they move off together at some unknown velocity. And, well, I know that since they stick together, that I know that their masses, you just add them together, and it's 2,900 kilograms. Yeah. So the question is, what velocity do they move off with afterwards? Just prior to, or just after the collision. So what we're going to do is take the momentum before. And that momentum before has two pieces. I've got the momentum, let's call this car A, and we'll call this car B. The momentum of car A plus the momentum of car B is going to equal the momentum of, let's just call this AB. So momentum of A is mass times velocity, so 1875 times its velocity of 23. This has a mass of 1025 and its velocity of 17. And this has a mass of 2,900 times its velocity v. So here I'm taking this whole idea of momentum before and momentum afterwards. I've got momentum beforehand, it's going to equal momentum after, only if I don't lose anything and there's no outside forces interacting. So I can go through the math and get each of these pieces here. So 1875 times 23, that's 43,125. Plus 1025 times 17, that's 17,425. And that's 2,900 V. So I can add these two things together, and I get 60550. And then I can solve this for V, and I get 21 meters per second. And I asked myself, does that make sense? Sure, it certainly does, because my first car was going pretty fast. So when my first car hits this one, it's going to slow down. So I know that my velocity is going to be less than 23. And then also, this one's going to get sped up. So I know it will always end up being between these two numbers. And 21 fits very nicely between those. Now, this also brings up a couple of, this is a certain type of collision right here. This type of collision is called an inelastic collision. An inelastic collision. An inelastic collision is any collision where they stick together and you lose kinetic energy. That's the real definition. And we can calculate kinetic energy. We'll get to this. It's 1/2 times the mass and velocity squared. So it's similar to momentum, and then it's mass times velocity, but it's doubly dependent upon the velocity. So if we went back to each of these things and we took 1/2 times 1875 times velocity squared plus 1/2 mv squared, add these numbers up, it's going to be more than this. Now, you might be familiar with the conservation of energy. We don't actually, energy is never lost. What happens is when these things collide, we lose energy to heat. That's the main one. And we lose energy to pieces flying, or we lose energy to sound. So that's a lot of times where the energy goes. Heat, sound, pieces. Now, if you get a collision where they bounce off, that's called, you might be able to guess it, that's an elastic collision. An elastic collision is something like golf balls are very close, super bounce balls. They're really, so they're exact, so if these things smush, these things are a bounce. And in an elastic collision, we have no kinetic energy lost. So let's talk a little bit. So this is a collision. So we kind of went through a collision. let's talk about a separation. What if we had a separation? Separations are exactly the same as collisions, except what you're going to be doing in a separation, you're going to have the event still, and you're going to have something that they're moving in opposite directions. So maybe it's like a person in a chair, and they're holding like a big medicine ball, and this person's they're on a frictionless surface. So, and then what happens is they throw it. So there's a person in a chair again, and they throw the ball, and the ball's moving this way. So the ball ends up moving to the right, but they end up moving to the left. So the momentum before will equal the momentum after. But the thing is, you have to define some direction as positive. Back in our initial last problem, we had everything moving in the same direction. Everything was moving this way, so the positive velocity, positive, everything was positive. The only difference with the separation is my momentum before, actually, it's 0. Because if my velocity to start with is 0, and then the momentum afterwards, this thing's moving this way, the ball's moving this way, you could give masses to you. Let's say this person is a 68 kilograms and a 10 kilogram ball. If you threw the ball, let's say, at 100 meters per second, which is pretty fast, I wonder what speed I would recoil at. This is the whole reason that shotguns, rifles, handguns, they kick. Or you spray a fire extinguisher, it kicks. You spray a fire hose, you're shooting a mass this way, it recoils and pushes you the other way. So for instance, momentum afterwards, I take mass times velocity, so it's the momentum of ball and the momentum of the person. My ball has a positive momentum. It's 100 times its mass, which is 10. And the momentum of the person is its mass times velocity, so mass of 68 times velocity v. And that's all going to be equal to 0. And it's going to be funny. So you take 100 times 10 is 1,000 plus 68v equals 0. So when I bring that 1,000 over, I get a negative 1,000 equals 68v. So when you solve this for v, you're going to end up with a negative number. So I get negative 14.7. Now that makes sense, because remember how we said that positive is forward. So this person's moving this way at 14.7 meters per second. So separations are identical to collisions, and just in the fact that something's going to have a negative velocity. And this is, I mean, and this right here is the entire reason that we have rockets. Like when you have a rocket, what a rocket does is it ejects material this way, which propels it that way. And it's really, I've got some really awesome videos online you can see of both separations and collisions. And a really unique thing, when they used to launch the space shuttle, when you watch that takeoff, it's so super impressive, because this thing, it literally launches 20, oh, what is it? I think it's 2,000 tons of material per second. So it's either 2,000 or 20,000. It's just an incredible, incredible amount of stuff being forced out the back, which gives you a recoil which propels it and accelerates it out of the Earth's atmosphere. And it's just absolutely incredible, because you think this takes minutes to get out of our atmosphere. How many thousands of tons of stuff are inside of this in fuel? So Collisions and propulsions both utilize before momentum, after momentum, only if it's a closed system and an isolated system.